Okay.
Yeah.
Okay, so we're going to introduce Youming, like he's going to continue talking about tensors and graphs. Okay, go ahead from here.
Yes, all good, thank you. Yes. Okay, so yeah, let's get started, and it will be, a continuation from yesterday's lecture. And yesterday we saw structures, right? About the tensors and graphs. And today we are going to say mostly like some questions and some techniques. So yeah, let's get started. And the first couple of slides will be just a review. So last lecture, basically we see recipes of constructing tensors from graphs, right? And after seeing that recipe, we see three correspondences of the structures. For example, on the graph side, we have this, we have perfect matching. That's the classical one. And then when you go to tensors, or matrices of linear forms, you see the non-zero determinant, right? That's a perfect matching and a non-zero determinant of matrices of linear forms. Then we also see isomorphism for graphs, relabeling the vertices so that two graphs become the same.
Youming, can I interrupt you for a second? I forgot to hit record. I think you might have to. I think you might have to say yes on your end or something like this. So.
Yeah, of course. Yeah.
Okay, perfect.
I think I said yes on the email, but.
Okay. I didn't know. I didn't know how it happened. So apologies for stopping you in the middle of your talk, but you're now recording.
Yes. Okay, so since we just started record, so that's the title page. Maybe I'll show that. So yes, to now basically just a review. So we last lecture we saw these correspondences between tensors and graphs. First, we have the recipes constructing tensors from graphs, and then we saw three correspondences of the structures. For graphs, we have the classical one, the perfect matching, and then on the tensor side, that's basically could trace back to two-timed low pass about a non-zero determinant. And we also see the correspondences between graph isomorphism, relabeling the vertices so that two graphs become the same, and the tensor isomorphism, you do change of basis on the, three or more directions, so the two tensors become the same. Finally, there are also independent sets on graphs and total isotropic space. We didn't really have time to talk much about this, but they are on the slides and they won't affect what's going on today. So we have seen some correspondences of the structures, and now this slide is just a quick review. Just a quick review of how you construct tensors from graphs. So at the very beginning, we were using the matrices of linear format, right? So every entry is a linear form in some variables. And then starting from graphs, we looked at two families of graphs. The first one is bipartite graphs. So that's this type of graphs. And the point here is that you are going to construct a matrix of variables depending on whether the edge appears in the graph or not. Okay. So for example, if 1, edge is in the graph, then you put a variable x11 here. If the 2, edge is not in the graph, then you put 0 there. So that's the bipartite graph going to a matrix of linear forms. And then in general, if you have some general graph, undirected and simple graphs without self-loops, then you're going to construct a matrix of skew-symmetric matrix of linear form. Also depending on whether the edge appears or not, right? So if 1, 2 appears, then you put x12 and minus x12 in these two positions. And if 2, 3 is not there, then you put 0. So yeah, that's a pretty naive recipe, right? But we see that this is useful from the algorithmic viewpoint, and we see that it leads to correspondences between the structures of our graphs and structures of our tensors. So that's just a quick review, just to refresh your mind. Of course, then we're going to some new stuff. So the first thing is that you probably have been bombarded by tensor isomorphism in yesterday afternoon. So I just want to mention to you that there are some practical reasons. I mean, not so practical for now, but hopefully in future. That is, there is a way to make use of tensor isomorphism in cryptography. So the story is probably some of you already know that. Basically, the story is that there is a post-quantum cryptography competition, initiated by NIST. And the background is that that our current internet security relies on factoring and discrete logarithm, IRSA, and Diffie-Hellman. So, and you also have been hearing probably a lot about this quantum. Sometimes it's say it's a hype, So, but indeed there are very concrete advancements and so on. So, but basically there have been some rapid progress towards building quantum computers, and because of Peter Shor's quantum algorithm for factoring and discrete log, it means that if a quantum computer was built, they would not be secure. The current internet security foundations will be shaken. So that's why NIST, National Institute of Standards and Technology of the US, started this post-quantum cryptography competition in 2017. And it has been going on, for 6-7 years. And last year, they initiated another call for the so-called additional digital signature schemes. And the reason is that they are not very satisfied with the current diversity of the security foundations of the digital signature schemes. Most of them rely on lattices. That's a mainstream method. But they want to diversify the security foundations. And it turns out there are 3 submissions to the NIST post this additional digital signature scheme call, including that. So you can see their website here. So including that, and the security foundation of MAD is essentially just 3 tensor isomorphism. Okay. So basically, if you can develop faster algorithms for 3 tensor isomorphism, about that, and they make use of random tensors. So if you can develop faster algorithms for 3 tensor isomorphism, you make some progress on understanding the security of maths. There's another one called ALTAC, so that's by me and my collaborators. We based on the so-called alternating trilinear form equivalence. So you will see that this problem is actually polynomial time equivalent to tensor isomorphism. So because they are equivalent, so you can imagine that if you have some ideas on this side, you may transfer to this side, and similarly the reverse direction too. So that's ALTAC. And finally, there is the so-called LAS. It's based on so-called code equivalence. It's the so-called linear code equivalence under monomial groups. So these three digital signatures, they basically follow the same design, and but they based on different isomorphism problems. And these 2 are in fact polynomial time equivalent. And this one actually reduces to them, but when it comes to very practical terms, this reduction, for example, these 2 are polynomial time equivalent, but the reductions usually involve gadgets, and as a result, the tensor you construct are very special, so they don't say much about practical settings, because in practical settings, people deal with random 3 tensors and all random alternating trilinear forms.
Youming,
yeah.
Is there a reason that isomorphism in general is a good choice for signatures? Forget about what the tensors are. If anybody had an isomorphism problem with X, is that generally how you make a nice signature?
Well, so yes. So first, I think there are 2 reasons. So the first reason is that there is a so-called Goldrat-Mikhaly-Wigderson zero-knowledge protocol, and the so-called Fiat-Shamir transform. So if you apply these are very classical protocols. These 2 protocols basically can apply to any isomorphism type stuff. So this gives you a passage from starting from any isomorphism problem you think are difficult, apply these two procedures, you get a digital signature case. Then there you need to do a lot of optimizations in order to make it practical in practice, like signature size and the efficiency when you are computing the signature, and also to verify your signature. But so the crypto part is pretty standard, I would say.
Okay.
You need to invent a lot of tricks. But on the other hand, so also with people, these are pretty classical protocol, which means that people know their security pretty well in general.
Right.
And then it boils down to solve, significant problems. So that's yeah.
Thank you.
So on the other hand, how the isomorphism problem is difficult, and you need to choose. Sometimes you need to choose. You may hope to choose, for example, the tensor carefully and so on. That's another story. But it basically finally it reduces to how hard your isomorphism problem is, and usually in the average case. Okay. So thanks. So we have seen these three submissions, and of course, there are different issues, obstacles for development to be done. But that's at least you see that it's coming to. You will see that it's coming like 3 tensor isomorphism. It's really embedded to the action. The three matrices acting on the three sides, they are really embedded in the code currently implemented. So, one last comment on this is that these problems, they will resist current quantum algorithm techniques by the work of Holgren, Moore, Rotella, Russell, and Sen. So essentially, they show that if you follow the standard techniques from Shor's algorithm, like the so-called cosine sampling, Fourier transform, and so on, you will not be able to make much progress on 3 tensor isomorphism, for example. Essentially, the one non-mathematical reason is that the irreducible representations of the general linear groups over finite fields as well as the symmetric groups, they are, of large dimension. So that's the mathematical reason for why we believe that the current quantum algorithm techniques won't work for these problems. Okay, so that's just some background, and to spice things up and to let you know that there are like very practical reasons to be concerned about the tensor isomorphism. So having introduced this background, but we are coming to the math side. This is like security and advertisement, and now we are coming to the actual math. So today I want to show you that the problems on graphs or the studies in graphs can sometimes lead to some interesting questions about tensors, and some techniques from graphs can also be helpful, or at least lead to something for the tensor side too. So that's the main message today. And I hope I can get to. I will give 2 examples. The isomorphism, right? This is what you have been, told a lot in these 2 days, and also perfect matching. So, but probably we won't have enough time to, cover the details in the perfect matching side. But at least I hope that I can show you the example from the isomorphism side. Okay. Okay. So for graph iso, we start with graph iso. So graph iso is a very intriguing problem in computational complexity. People have been studying it since, I don't know, 1960s, 1970s. And one of the, there's even, some interesting fact or story. That one of the founding fathers of the P versus NP question is Levin, right? Leonid Levin in the Soviet Union. And one motivation of him introducing P versus NP is because he wanted to understand the complexity of graph iso. So of course we know that graph iso is kind of NP intermediate, so it's not really NP complete. So but that's kind of like a byproduct of studying graph iso, this P versus NP stuff. So and another thing people have been studying about graph iso is that there's a so-called universality of graph iso in the testing isomorphism combinatorial structures, which basically suggests that there are isomorphism problems, for example, for directed graph iso. hypergraphizer, also called line graphs. Or sometimes it goes to a little bit exotic, like homeomorphisms of two complexes. It turns out these problems are polynomial time equivalent to graph isomorphism problem. So most of the reasonable or even some special structures of special combinatorial structures, they turn out to be polynomial time equivalent to graph iso. So this is the universality, right? Graph iso seems to be occupying a central position in all the problems, or at least in many problems, in testing isomorphism combinatorial structure. So this then leads to the kind of a natural question is, what is the role, what would be the role of tensor isomorphism in the realm of testing isomorphism of algebraic structures, right? So we are hoping to show that it's also somehow versatile in some sense. And of course, for algebraic structures, we don't lack isomorphism problems, like polynomial isomorphism, group isomorphism, and algebra isomorphism, and so on. So we will see. Okay, we will see that their definitions later on. So that's a hope. We hope to show that tensor isomorphism will play a role similar to graph isomorphism in the combinatorial world. And here, by universality, you can, of course, we need to define what universality means, right? Actually, you can define it in two ways. Because today I'm talking to mathematicians, so I use the so-called containment of orbit structures proposed by Gelfand and Panamero in the 1960s, 70s. So what does that mean? So at some point, Gelfand and Panamero, they wanted to study the so-called orbit structures of different group actions. Okay? And then they could propose this very natural definition. So suppose you have two group actions, G, a group G acting on a set S, and H, another group H acting on a set T. We say that the latter action contains the former if there exists a map from S to T, the set, that preserves and respects orbit. So you can imagine that the S, because of the group action G, is partitioned into orbits, right? And we say that the action, the G action, the H action contains the G action if you can have a map between S and T such that the orbits of the S side will be mapped to the orbit of T side. So for example, this won't be allowed, right? So you cannot have an orbit here that mapped across here, or you can map two orbits in the same orbit of T. So that it just preserves and respects. What does preserve and respect means? So this is the containment relation between group actions, and they propose in the context of representation theory of associated algebras. And this definition also leads to the so-called tame-wide dichotomy in the representation theory by Joy. Okay, so that's the containment relation between group actions. Now let's take a look at the several isomorphism problems for algebraic structures. So probably some of them are already covered. But I'll just do it very quickly, okay? And the point is to let you know to reveal that many of these problems are basically encoded by tensors, but under different actions. Okay. So first, let's review a little bit about group isomorphism, the P groups of class 2 and exponent P, and via the so-called Bayes correspondence. And it turns out that this problem is essentially equivalent to the following problem, for the skew symmetric bilinear map isometry. Here you have two vector spaces, U and V, over, let's say, over Fp, the finite field of order P. And then the input of this problem then will be two bilinear maps from U cross U to V. And of course, these two bilinear maps are said to be isometric or isomorphic if there exists an invertible matrix A in GLU, well, and another linear transformation B in GLV, such that essentially A acting, A naturally act on the U side, B naturally acts on the V side. That is, for any U and U prime, F, when applied to A transform U prime, will be the same as E applied to GU prime. Okay, so this is just the two bilinear maps being isomorphic or isometric. So of course you know that now that if we fix spaces for U and V, then we can store the bilinear map U cross U to V as a three-way array, right? Then the three-way array will be of size n by n by n. So n is the dimension of V, n will be the dimension of U, and essentially the ijk entry of F, of this three-way array F, will be the evaluation of F on the I standard basis vector and J standard basis vector. Then you take the case component, because SEIEJ will be a vector in V, right? So it's of length n, and you take the case component. So that's how you record bilinear maps, for example, in algorithms. Okay. So now we see that what the isomorphism problem now is, right? So the isomorphism problem is that you have two bilinear maps recorded in three-way arrays F and G, and you have an invertible matrix, n by n invertible matrix A, acting on the left side as well as acting on the right side. Then you have another invertible matrix n by m size B, doing linear combinations on the m side, right? So this is the isomorphism problem for skew symmetric bilinear map, and the motivation is actually to tackle group isomorphism. Okay, so this is the group isomorphism and the resulting the three-way array and the group actions. So that's a group side. Now, another thing is about this so-called algebra isomorphism. For algebra isomorphism, now we only have one finite dimensional vector V over a field F. And now the input are also bilinear maps, but now it's not U cross U to V, but it's V cross V to V. And then the question is that there exists an invertible matrix A or a invertible linear transform A, such that when you apply A on this side, and then of course A now applied on this side, such that the two bilinear maps are the same. Okay? So it's quite similar to what we just see, but the action is somewhat different because now we have only one invertible matrix A acting on the three sides. Okay. So this is the algebra isomorphism. Of course, for algebraists, you would like to impose conditions like alternating associativity, Jacobi, and so on, so that you get associative algebra or Lie algebras. And this has been studied in theoretical computer science and in computer algebra by these people, Agawa, Saxena, Groucho, and of course James and Peter. So that's algebra. So computing with algebras is also a big topic in computer algebra. So for example, Romain, Ivanush, and William de Graaf, they have been studying this. There are monographs about this. So there, when people talk about computing with algebras, usually there are several representations of algebras. But at least one representation is the so-called by structure constants. And by structure constants, you can imagine that this is again, structure constants is a tensor or three-way array, right? Now it's n by n three-way array, and the ijk entry of this three-way array F will be F applied on EI, EJ, and the case component, then take the case component. So now we see that what algebra isomorphism means. The algebra isomorphism means that you have two cubes, right? Yeah, it's not cuboids anymore, and then you have the same matrix A acting on the left and right side, and then A acting on the third side of G. So that's algebra isomorphism. The last one is the so-called cubic form equivalence. Now we are going to polynomials, right? So the cubic forms, of course, are just homogeneous degree 3 polynomials. And we have two cubic forms, f and g, and in n variables. And then we want to know whether, by doing linear combinations of these variables, then there exists a such that when you do linear combinations of variables, you change polynomial g to polynomial f. Okay, so a cubic form equivalence actually has a very interesting origin. It actually has been studied in the so-called multivariate crypto since the 1990s. So it has been studied pretty, well, not very intensively, but at least some very serious work over there. Okay, and from cubic forms, we can also build some tensors. And this is, just by going from cubic forms to the so-called symmetric trilinear forms. And here we impose that the characteristic of the underlying field is not 2 or 3. And then F you can view, F as a cubic form, you can view it as a map from F to the N to F, right? If you assign these xi's with values, it's essentially a function from F to the N to F. And then you define. Yeah.
Are these homogeneous, Youming?
Sorry, I didn't hear.
Is your cubic form homogeneous? Is that what you mean by saying it's a cubic form?
Yes.
Okay.
Exactly, yes. Form is usually, I think people could take it as homogeneous. So degree 3 homogeneous polynomials. Yes. No worries. Okay. So you start from such a function. Then you can define the so-called symmetric trilinear form. This is essentially what you do when you want to symmetry your matrix, right? If you have a matrix, you want to symmetrize it, you define A plus A transpose divided by 2. So this is kind of the same procedure, but extended to the degree 3 setting. And then you can have this, you use this formula, but at the end of the day, you get some trilinear form. Once you get a trilinear form, okay, now it's again the tensor or three-way array kicks in, and then you can define a three-way array F, and the ij case entry of F will be the evaluation of this F hat, this symmetric trilinear form on EI, EJ, EK, where EI, EJ, EK is their standard basis vector. Once you put this into a trilinear form, into this three-way array setting, now we see what cubic form equivalency can be formulated, right? This A now is a little bit different. This A now is acting on the three sides of F at once. So now you are given these two tensors or two three-way arrays. You want to know whether they are the same. Under A acting on the three sides of F, then transform F to G. Okay. Now we have seen, so this is a brief recap, okay? So we have seen group iso, right? And it gave us bilinear maps of this format, U cross U to B. We have also seen algebra iso, which gave us the bilinear maps of, say, U cross U to U. And we have also seen cubic form isomorphism by going to symmetric trilinear forms. You get U cross U to F. Okay, and then you see that the difference lies in that you always have some three-way arrays of some format, n by n by m or n by n by n, but the actions are different actually. Like you have A acting on these two sides, B acting on this side, or you have the same A acting on three sides, but two of them acting on F, one of them acting on G, or three of the A's will act on F. So from different algebraic structures, you get tensor isomorphism, but under different group action, right? Okay. Now, of course, the question is, are these group actions, different group actions on tensors, are they comparable, right? Are they, for example, equivalent under the containment relation by Gelfand and Penrose-Merrill? So now we want to understand, let's compare maybe group ISO, algebra ISO, and cubic form ISO. Okay? And as a warm-up, so you know that these are the tensor settings, so it's essentially a continuation of the matrix setting or generalization of the matrix setting. So as a warm-up, let's think about, can we compare the following matrix problem? For example, if you talk about the so-called matrix equivalence from your linear algebra course, essentially you are looking at linear maps from U to V, where U and V are different vector spaces. And then if you talk about matrix conjugacy, then you are talking about the linear maps from U to U itself. And then you can ask, of course, whether these two group actions under matrix equivalence and matrix conjugacy, are they somehow comparable or not? So for convenience, let's think about dimension U being equal to dimension V being N, let's say, and over algebraic closed fields. And for matrix equivalence, it's an easy result in that essentially two matrices are equivalent under GRU and GRV if and only if their ranks are the same. So which means that because they are n by n matrices, you have only n plus 1 possible ranks. So the number of orbits is finite, n plus 1. But on the other hand, for matrix conjugacy, this is classified by Jordan normal form, right? Because of Jordan normal forms, here you essentially by looking at the eigenvalues and so on, you have infinitely many orbits. So this seems to be suggesting that okay, matrix conjugacy is more complicated than equivalence, right? Here you have finitely many orbits. Here you have infinitely many orbits, and then you have also the Jordan block structures and so on. So, which seems to suggest that, okay, at least in the matrix case, it seems you cannot have this containment relation between matrix equivalence and matrix conjugacy. So this is what we learned in the matrix setting, and also to let you have a brief idea of what will happen for the 2x2 set, for the two tensor setting. Now, interestingly, when you go to three tensor setting, the story is quite different. So it's in a series of these works. So it turns out that for the three tensor setting, then the following actions on three-way arrays, they are actually equivalent under containment. For example, when I talked about tensor isomorphism, which correspond to the trilinear maps of the form U cross V cross W to F. Then we also talk about the bilinear map isomorphism, right? That's the U cross U to V. That's where we get from the P group setting, P group isomorphism, especially with skew symmetric. We also have the so-called trilinear form isomorphism. So the trilinear form isomorphism is U cross U to F, which is essentially which has its origin in, for example, cubic form equivalence. And finally, for algebra isomorphism 2, that's the U cross U to U setting, and the algebra you can even assume that they are linear associated. So then you say that, so two remarks. First, the constructions are efficient. I state here as under containment, but that's the one way to compare orbits. Another way, for example, you can, in computational complexity, you care about polynomial time reductions. So these equivalents under containment, actually, they also give you polynomial time reductions for these, between these different isomorphism problems of tensors. And for example, you can say that classifying cubic forms and the algebras are equally difficult, because of this equivalent of the containment. And just to note that this is in contrast to the matrix case, because for the matrix case, you have you cannot really compare. They are incomparable. The matrix conjugacy, matrix equivalence, they are incomparable. But when you go to the 3-tensor setting, everyone suddenly becomes equivalent. Okay, so that's the first result I want to mention. And the second result is also, I think, pretty interesting. So we have been, so far, we have been mostly looking at 3 tensors or 3 real arrays in this lecture. But of course, you can also consider the so-called K-way arrays, right? So if you have K vector spaces over a field F, then you have the general linear groups of this U1, U2 up to UK acting on the K tensors. And then what will happen? So there's another result which said that the 3 tensor action actually contains the 10 K tensor action for any K larger than 3. So essentially it means that when your K starting, so 2 is easy, right? 2 is just matrix equivalence. 3 decided by rank. 3 start become tricky, but when you go from 3 to 4 to 5, it doesn't become trickier. And they are polynomial term equivalent to the 3 tensor case, or reduce back to the 3 tensor case. Okay. So yeah, just to recap, we see that 3 tensors are more difficult than 2 tensors, right? For 2 tensors, they are just matrices. But when K is larger than 3, the orbit structures do not become more difficult. So this is kind of a good thing for us if you just care about worst case complexity. Now you just need to have like 3 tensors, you can still draw it because you will have 3-dimensional space, so we can still draw it and reason about it.
Youming,
And yep.
the K in this is constant for that reduction?
Well, yeah, the K should be constant, and at the end of the day, if you start with, say, K tensors with every vector space of dimension n, then the resulting 3 tensor will be of dimension, say, n to the k by n to the k by n to the k.
Okay.
So it's n to the 3k, which is polynomial in the dimension, polynomial in n to the k, but it's actually it's a big blow up, but it's polynomial blow up. So yeah, I'll prove that.
Thanks.
Nice. Yeah, just one last comment is that the proof makes use of path algebras from representation theory. Okay, so hopefully now I think this works. Here to clarify a little bit, the complexity landscape of TensorFlow, and also somehow partially, indicate that maybe or probably TensorFlow could play a unifying role in testing isomorphism of algebraic structures like groups, polynomials, algebras. And then I want to talk about the techniques, right? So we have seen 2 techniques, basically for relating 3-way arrays under different actions. We mainly use 2 types of techniques. One technique comes from Gelfand and Pelon-Merat, and the other technique is so-called gadget method from computational complexity. So the gadgets we use, now we have 2 types of gadget, but at least the first gadget, it actually originates from this paper by Futerni, Sergeychuk, and Qiao. So these gadgets are reminiscent of those used for the so-called color graphizing. So this is where I want to demonstrate to you that some ideas from GraphISO may be useful even posteriorly, but will be useful to understand tensors. Okay, so what is color graphizing? So suppose we have 2 graphs, right? And suppose their vertices are also colored. Some of them are red, some of them are blue, right? And now we want to find isomorphisms between these 2 graphs that also preserve the colors. Namely, we want to find isomorphism of graphs where the red vertices should be mapped to the red vertices, and the blue vertices should be mapped to the blue vertices. Okay, so this is a so-called color graph ISO in computation complexity. It's a pretty standard and important problem in the theory of complexity theory of graph ISO. So, and then the one question is, can you reduce colored graph ISO to ordinary graph ISO, namely where graphs are not colored? So here is one solution to this reduction from colored graph ISO to graph ISO. Namely, for example, we want to make these red vertices special, right? How to make them special? For example, one important invariant about graphs is the degrees, right? About the vertices of the graph is their degrees, namely their number of neighbors. So this leads to the so-called star gadgets. The star gadget said that you can add a bunch of extra vertices, and then say if the graph is of order n, you add, I don't know, n plus 1 vertices, and then you connect them to the red vertices. So if you do that, you see that the red vertices will be of degree at least larger or equal to n plus 1. On the other hand, the blue vertices will be of degree at most n. So this gives you a distinction between the red vertices and the blue vertices, which means that you have to map the red ones to red ones. Of course, you do the same gadget on each side, on both graphs, so that because of degree, you have this distinction between red and blue. So when you do graph ISO on these extended graphs, the red and blue colors will be automatically preserved without this color information. So that's the reduction from colored graph ISO to ordinary graph ISO. So then we will say that such a gadget will be useful if you want to reduce tensor ISO, right? U cross V cross W to F to skew symmetric bilinear map at most level. For skew symmetric bilinear map, you have S cross S to T, where it also should be skew symmetric. And we want to, starting from such bilinear forms, then we are going to construct bilinear maps such that these two trilinear forms or tensors are equivalent under the action of 3 invertible matrices, if and only if these two bilinear maps are equivalent under the action of 2 general linear groups. Okay, so let's see. So if you think about it, you will probably see that, okay, there should be some very natural construction. Why that? Because if you start from F, right, then you fix spaces for U and UVW, and you know that at the end of the day, this F will be a 3-way array. Let's call it A. And if the dimension of U is L, dimension V is N, dimension W is M, you have L by N by M 3-way array. And because you also want to get, at the end of the day, you want to get skew symmetric matrices. So nowadays are just like blocks. These are blocks, then you permute them and add them and make another copy and so on. So then this leads you to this construction, right? So you put A here, then you put the inverse of A transpose here. So this makes it skew symmetric, right? And then you put 0 and 0 on these two sides. So now you see that S is a direct sum under U and V, and on the third direction is still T equals W. Okay, so they're just, now you're playing with blocks. And these entries will be 0. Okay, so this is a very natural starting point. And we have done this. We have just starting from some block here. We make an inverse A transpose. I mean, look at the frontal slices, you do the inverse and transpose. You put the other block on this side, so you get this N plus L by M, N plus L, n plus L by n plus L by M tensor, or three-way array. Okay, so now we have gone from tensors to bilinear maps. But if you then think about it, there will be an issue. Namely, here we are looking at GLS, right? GLS is GL U direct sum V. But on the other hand, for here, we only allow GLU and GLV. So this basically means that GLS, where S is U direct sum V, will mix up U and V. At the end of the day, we want this to be somehow block diagonal, but if you just put it plain naively like this, you cannot impose that the GLS does not mix the U slices and the V slices. So that's the problem now we want to resolve. Okay. So at the end of the day, we think that okay, we come up with a solution, and the solution is that we want to. So now you say that the problem is that you want to make the U slices and the V slices to be distinct, or they are special in their own way. And our construction is essentially very, it has a very direct correspondence with the star gadget in graphs. Namely, how do we make, for example, these horizontal slices special? You add large enough identity matrices to them. You add enough identity matrices to them, so the ranks of the horizontal slices for the U side, will be controlled in some range. You see that the identity slices here are of size 2n plus 1 by 2n plus 1. Then for the slices from the U side, you add identity matrices of size 4n plus 2 by 4n plus 2. So then their ranks will be distinguished, and then this give you, this will help you to distinguish the U slices and the V slices, so the GLS cannot mix the U slices and the V slices arbitrarily. And this turns out to be the construction that suffices for our purpose. So this is essentially, the construction itself actually has a very direct correspondence with the so-called star gadget. Okay, so that's what I want to talk about TensorISO. And on the TensorISO side, I think the main message is that first you have this. I'll go back quickly to. Yes, for the TensorISO side, the main message is that TensorISO isomorphism is equivalent to several, natural isomorphism problems for algebraic structures. Like, so here it's about P groups, and if you look at this, it will be about cubic forms, and it's also about Lie and associative algebra isomorphism. So we are hoping that TensorISO will play. I think there are still many questions to consider on this front, but we are hoping that the TensorISO will play a hopefully unifying role in the isomorphism problem for algebraic structures. Another thing is to note that the 3 tensor action contains the K tensor action for K larger than 3. So, which is a good news, because for 3 tensors I can still think in terms of the 3-dimensional space and so on. So that's the TensorISO side. Any questions so far? Okay, if no question, as I was saying, probably we don't have enough time to talk about the perfect matching side. Okay. So, but I'll quickly mention that some of the perfect matching and non-zero determinant. Okay. So we have seen that for bipartite graph, we see this relation, right? G has a perfect matching if and only if the determinant of the matrix of linear form associated with this G is not identically 0. Okay? And so that's from the last lecture already. The point is that there is a so-called Hall's marriage theorem, which is also a pretty basic and standard result in combinatorics now. That is, bipartite graph G has a perfect matching if and only if G has no strong subset. Okay. What is a strong subset? A strong subset is the set of left vertices such that their neighbor size is smaller than its original size. For example, if you look at these two vertices on the left side, you see that their neighbor is only this vertex on the right side. So this is a strong subset because its neighbor size gets smaller, right? So this is a very basic result by Hall called Hall's matrix theorem that G has a perfect matching if and only if G has no strong subset. The story for the perfect matching side is that we have seen the correspondence between perfect matching and some property on the tensor side. But for graph side, you have perfect matching and strong subset. They are like the opposite structures in the graph case. Then the question is there a linear algebraic correspondence of strong subset in the algebra setting, in the tensor setting? It turns out that there is something called strong subspace in the tensor setting, which basically has a nice correspondence with graph 2. Okay. Because of time, I'll just tell the story, and I'll share the slides later. So if you're interested, you can take a look. Okay. So this is just to say that on the tensor side, there's also some structure corresponding to the strong subset structure of graphs called strong subspace. And this strong subspace problem, then you can formulate, for example, strong subspace problem for general tensors rather than the tensors deriving from graphs. And this strong subspace problem turns out to be quite significant. We have seen a significant progress on the strong subspace problem in the past, 7-8 years. So, and the strong subspace structure turns out to have deep roots in invariant theory, non-commutative algebra, analysis, through the broad swap scram leap inequality. So it's a pretty funny structure, It's pretty. If you look at the definition of strong subspaces, it's a quite basic linear algebra stuff. But it turns out to have relations with several branches of mathematics, like invariant theory, non-commutative algebra, and analysis, and so on. And there's also a big progress on understanding the complexity of strong subspace problem. We now know that it's actually in polynomial time by 3 algorithms. First algorithm is by analysis, in the analysis flavor by Garg, Guvitz, Oliveira, and Wiggerson. The second one is by me and collaborators Gabor Ivanush and Kevin Subramanian. And the third algorithm is by Hamada and Hira. This goes to the optimization algorithm on the cat-zero spaces and so on. So just saying that the strong subspace problem seems to be quite, it has relations with many mathematical functions, and we have seen progress of strong subspaces in the past few years. And another surprising, because we have been mostly talking about tensor isomorphism, right? So another kind of surprising connection is that this strong subspace problems turns out to be useful in the tensor isomorphism algorithm by Xiaorui too. So Xiaorui had some big breakthrough last year on the worst case algorithm for tensor isomorphism, and it turned out at some point his algorithm is actually can be used as computing the strong subspaces. So this is just saying that this type of structures now they seem to be emerging everywhere, and then we're also seeing connections between shock subspaces and, for example, tensor isomorphism. Okay, so I'll just stop here and I'll share the slides. So this is a problem side, and the technique side, basically, I want to mention that there is a so-called linear algebraic analog of the so-called alternating path method. But I don't think we'll have enough time to go through this now. I'll share the slides. In fact, if you look at the slides, I have two versions, okay? I have the first version about setting up the analogies or connections between on the graph side and on the tensor side. And if you go through to the last few, so if you go to the after, thank you, you have another version about explaining our method and how it compares with the linear algebraic alternating path method. The alternating path method in graphs. Okay, so I hope that after one of these versions will be here for you if you want to understand the linear algebraic analog of alternating path method.
Okay. Thank you, Youming, for both talks. And are there any questions? Okay, first, okay. Great job.